Let's begin with our first subtopic, a set theory. Okay, let's ask first question. What is a set? Set is a collection of different objects. You can think of it as a basket consists of several objects A1, A2, A3. Think of these things as some set of fruits. A1 can be an apple, A2 can be an orange, A3 can be a mango. Now, in mathematics, it's easier to write instead of drawing basket or something, easier to write using curly brackets. So essentially, these curly brackets together represent a basket, and the elements or the objects inside the basket are typically represented by letters, English letters. We call them elements of set A. For any given set A, we use A belongs to A or A in A to denote that A is an element of set A. For any set, say A, the number of elements is called cardinality of that set and denoted like this. For example, in the above example here, we have n elements, A1 to An. So the number of elements is n. Cardinality of a set can be finite or infinite. When it is finite, we call that set finite set. Examples include, suppose you take set of integers 1 to 5, then this is a finite set which has only 5 elements. Or you can have a set which has two objects or two elements, two strings, here fun and sad. Or you can even have a set which consists of other sets. So 1 and 3, 1 2 is a set, and 2 3 is another set, and A is a set that consists of these sets. You can also have infinite sets when cardinality of that set is infinite. For instance, you can take all the natural numbers 0 to all the way up to infinite, that is typically denoted with this n, or you can have all the integers denoted with z, or bigger set like all rational numbers we denoted with q, or all the set of real numbers. We even allow a set without any elements. Such set is called null set or empty set, denoted by phi, which is essentially a basket without any elements or brackets without any elements in them. There is another set that plays an important role in set theory. We don't talk very often, but it is present in every time we talk about sets. That is called universal set. For instance, if you're working with integers, you can think of universal set, typically denoted as S, is a set of all the integers. In case you are playing with real numbers, then even though you're considering a finite set of real numbers, you can think of S being a set of all the real numbers, R. Venn diagrams are quite useful for conveniently representing the relationship between these sets. For instance, you have a universal set S that is typically represented as a rectangle box, and you have a couple of subsets of this S, this universal set S. Let's call them A and B. For example, S is set of all the real values. A can be just consider numbers 1, 2, and say B is 2, 3. Then what we have here is 1 here, 3 here, and 2 is a common element, so you have here. So this is the understanding behind Venn diagram. Okay, once we have such a representation or understanding, we can talk about more relationships. First relationship is subset relationship. Let's call we have two sets A and B, and we say that subset A is a subset of B, denoted as like this. if every element of A is also present in B. For instance, you take set A, which is set consists of numbers 1, 3, and 4, and also consider set B, which consists of numbers 1 to 5. Clearly, all the elements of A is also present in B. So, A is a subset of B, and we denote that such relationship in Venn diagram as follows. Where you see that A is sitting inside the B because A is a subset of B. Also note that a null set is a subset of every set. It's clear intuitively why that should be the case. Another relationship between two sets is intersection. Let's again consider two sets A and B, and intersection between two sets is denoted as follows, which is the set consists of elements that are present both in A and B. So this is the definition of A intersection B. What is it saying? A, consider all the elements A such that A is in A as well as in B. So this region denotes intersection between A and B when you're looking at Venn diagram. There is another relationship between sets that is intuitively opposite to intersection, that's called union. Let's consider again sets A and B. Then union of A and B is denoted like this, and the definition as follows. A union B is a set of elements A that are present in A, or, this is important, or in B. And when you represent A union B in Venn diagram, this is how you represent in this figure as shown, this green region, which you can see that consists of all the elements present in either A or B. In general, the intersection relationship can be extended to multiple sets. For example, you have n sets, let's denote them A1, A2, all the way to AN. Then we can define intersection between all these sets written like this, or in a compact manner written like this, which is essentially is a set which consists of elements that are present in all these sets. Similarly, we can extend the union definition also to multiple sets. I can consider n sets A1 to AN, then union of all these sets can be represented like this, or in compact manner can be written like this, which is essentially a set consists of elements that are present in at least one of these sets. Another operation which we don't use often but sometimes very useful is called set difference. Let's consider two sets A and B. We denote set difference A backslash B, or sometimes we just denote it as A minus B, which is the set of elements that are present only in A but not in B. So in mathematical definition, A minus B is a set of elements that are present in A but not in B. When you look at a Venn diagram, corresponding Venn diagram, the region, this region represent A minus B. As you can see, you take away all the elements which are present both in A and B, and consider only elements that are present in set A. That gives us A minus B. Similarly, B minus A can be defined, that is this region which consists of elements that are present in B but not in A. Another set that is quite useful for us is complement of a set. Let's consider set A. What is its complement? A complement of A is essentially all the elements present in S but not in A. So you're looking at all the elements that are outside A. That set is called complement of A. Here, in this Venn diagram, this region, the region I'm highlighting, represents the complement of A. This is a very brief overview of set theory. Of course, we can't cover all the details here. So I recommend you to have a look at other materials if possible, because set theory plays a very crucial role in defining events and probability of those events. We will see how it is done in the next video.